Hello everyone, greetings of the day. Myself Dr. Jenifa from Department of Computer Science and Engineering Artificial Intelligence, and today in this video we are going to see backpropagation in deep learning. To start with, what are the slides or the contents we are going to see in this presentation are introduction to deep learning, what is backpropagation, so introduction to the backpropagation, the mathematical foundations involved in the backpropagation, neural networks and backpropagation, gradient descent algorithm in calculating the backpropagation, and then at the end we are going to see one example with some numerical calculations. This is what we are going to cover in this video. First, when it is coming to the introduction of deep learning, everyone know it is one of the sub part of our machine learning. So where this deep learning uses a neural network, artificial neural network, to process some massive amount of data, a huge amount of data. So that is one of the main difference between our machine learning and the deep learning. The difference is when it comes with massive amount of data, we can go with the deep learning. So there we will be using this deep learning. And then in deep learning, we are having multi-layered neural networks because it is considering some set of layers like input layer and then one or more number of hidden layers and then output layer. So with this, we can enable that hierarchical learning in our deep learning. And next thing is it is automatically extracting the feature, which is one of the main advantage of our deep learning. Then as we discussed earlier, it is dealing with large amount of data, so it is very good for that. The another one important thing what we are going to discuss today is the backpropagation algorithm. So it is trying to adjust the weights based on the errors we are getting during our progress. So it is trying to reduce the error by adjusting the weights. For that we are using the backpropagation algorithm. So any kind of real world applications, for example, speech processing, audio video recognition, image recognition, natural language NLP based applications, or any autonomous systems, this deep learning plays a very important role. Now coming to our today's topic, backpropagation. So it is nothing but a supervised learning algorithm, and it is trying to train the ANN, that is artificial neural networks, to adjust the weights. Why I have to adjust the weights? So obviously when we are creating a model, it predicts something, but actually the expected output will be a different one. The target output will be a different one. When this scenario happens, this kind of problem occurs, so our model, our backpropagation is trying to update the weights based on the errors at the end of my output layer. So how it actually works, starting with the input layer to the output layer, it is doing the forward passing. So starting with the input, which can be any kind of input data, then a set of hidden layers, and then at the end is our output layer. Now at the end of the output layer, we are trying to calculate the error, which is nothing but the expected versus the predicted. So with that, if there is any error, then we are going with the backward propagation, that means backpropagation. So with this backpropagation method, we are going to update the weights, and this new weights will again be proceeded with the forward pass. So this is what the main steps in our backpropagation. So how this deep learning get benefited, deep learning models get benefited with our backpropagation is when we are trying to self-optimize the models so that to improve the accuracy. So by that time, we can use the backpropagation. So can I stop this just with one iteration, means only one time I am updating the weight? Can I stop? No, until we are getting the expected output, or at least very near to the expected output, or in another words we can say the very reduced, the very minimal errors. So until that we are trying to do the backpropagation. So that is what the main importance of our backpropagation. So whatever the model we are developing, to make the model to learn efficiently, backpropagation plays a very important role. So mainly I have listed here few points why the backpropagation are important. So first one is it automates the learning because we are automatically updating the weights, right? So to reduce the error. So the automated learning can be done by using the backpropagation. So the weight optimization will be an efficient one because we are working in the backward way based on the error we got, right? So it will be an efficient way to optimize the weights. As our deep learning will always go deep in learning any data, this backpropagation will go through all the layers of our architecture. Hence, it enables the deep learning to work efficiently. And it is trying to reduce the error, right? So obviously, our accuracy will be improves. Whatever the application we are working with, this backpropagation will provide a much efficiency and maybe if there is no backpropagation, if there is any error which is very high, that means predicted versus the actual, if it is very high, really our models, our deep learning models will struggle to learn by itself and to update the weights because that should be manually done, right? So that will be a problem. So these are all the main importance why we are going with the backpropagation. Now coming for the main important part like mathematical foundation, why we are whatever the terms we are going to use here. Mainly, we'll be using here the calculus and linear algebra to update the neural network weights. Okay, so what are the formulas we are going to use here is loss function. So once at the end of the forward pass, we try to calculate the error, right? So for that, we'll be using this loss function. In the upcoming slides, we will see different types of this error measurements also. Then gradient descent to update the weight, we will be calculating this gradient descent, which is nothing but dou L by dou W means the loss, the error with respect to which weight. Then the chain rule, when we are backpropagating from the error to the output layer, then output to the hidden layer. So we'll be using the hidden chain rule to calculate those differentiation. So next, neural networks and backpropagation. So before getting into the backpropagation, we have to know a little bit about neural networks, right? So as we have seen in the third slide of our network, of our PPT, so this neural network consists of some set of layers where the input layer receives the raw data, which is in the form of image, a text, or any audio, video, whatever it may be. Then the hidden layers, which may be one or more number of layers based on the model what we are choosing, then it processes through that connections and the information are passed between one node to another node through this hidden layers, the processed information. And then the output layer, this is the layer which produces the final prediction. For example, if I am doing some model for dog versus cat, whether it is a dog or cat, that is the final prediction, right? So that is what done in the output layer. So this is how the flow is going to happen in any neural network. Now, gradient descent algorithm, how and why this gradient descent algorithm is. So after computing the loss in our model, once the forward pass completed, the second step is to compute the loss. So once it is completed, then we have to calculate the gradients with respect to the weight, right? So for that, we will be using this gradient descent, where here this formula will be like a W new, that is the new weight is equal to old weight minus eta, it is nothing but the learning rate, then dou L by dou W. So this is a gradient which is going to work on updating our weights. So this process will be repeated until we are getting a minimal error or the actual and predicted outputs are going to be the same one. These are some of the examples like where the different kind of activation functions we are using, sigmoid ReLU and which this formula which we have already seen in the previous slide itself. Okay, so next comes our forward propagation pass. Why this forward propagation pass important in our backpropagation is, first I have to start with any kind of neural network model. First we are going to start with the input layer, okay, and then I'm going to calculate the weight. That means at the end of my input layer, what information is going to pass to the hidden layer? The first hidden layer is nothing but W star X plus B, where W is nothing but the weight to reach from X to the hidden layer. X is nothing but the input neuron, and then B is nothing but the bias. So this is what the information passed from the input to the hidden layer. That means the next level. So for that, we will first apply the activation function, where this activation function can be of anything like a ReLU, sigmoid, or a softmax. So this output will be passed to the next layer, whereas maybe in case if I don't want to apply any of this activation function, as we all know, this activation functions will include the non-linearity in our forward propagation, which will make the enabling process much good. That is the reason we are using the activation function. So in case if you think it is not required, yes, we can omit this step. So why this forward propagation is required in our back propagation or backward passes? First, without calculating the error, is it possible to propagate back? Because we don't know whether there is an error or not. Should I back propagate or not? So to enable that, first we have to do the forward propagation. So once I reach this final output layer with the error I am getting, so I am going to move to the previous layer, that is hidden to input. This is how the back propagation will work after applying the forward propagation or the forward pass. So what's the loss function? I mentioned in the previous like what are the different kind of loss functions that can be calculated in deep learning model. First one is mean square error and cross entropy loss. So here we will be using the mean square error as we are going to consider the example of regression. So that is why we are using any kind of the loss function can be used. With this, we will be finding the error at the end of output layer. So what is the role of this error calculation or the loss function in backpropagation is? So first, it is giving us the error. It is helping us to calculate the error, and then it is giving us the guide to update the weight based on the error, and hence it is enabling the learning by minimizing the error. So that is the importance of loss function, to calculate the loss functions in backpropagation. So now we are coming for the steps in backpropagation. So first one, as I mentioned, we are going to start with the input to the output layer, forward pass. So once it is over, I'm going to compute the loss, that is the error. Now starts our backpropagation. So I'll be starting with the output layer, then gradient calculation. Based on the gradient calculation, we are going to update the weights. Okay, so this is what the steps we are going to follow in the backpropagation. So with this, we are moving for the examples, step-by-step examples involved in our backpropagation. Now for this example, I'm considering a very simple, just only one hidden layer is available. Okay, a very simple example to update the weights. So let us go to our example. Let us consider this input where I'm having the input layer x1, x2. So this is the input layer. X1, x2 are nothing but the input layers. And then I'm introducing another one layer, h1, h2, then only one output layer. Or I can say only one output neuron. Okay, so from here, x1 depends on the input from x1 and x2. Then from x1 to h2, x2 to h2. And when it comes with my output layer, so this is what the input we are considering, the neural network we are considering here. So now let us assume the value. Okay, so for let me use different color so that it will be easy to identify. So I'm having 0.35 for x1, 0.7 for x2, and then here. I'm assuming the weight here is 0.2. Then this also 0.2. Here 0.3, 0.3. So from H1 to O means output neuron. Okay, so H1 to the output neuron, I'm assuming the weight is 0.3 and this weight is 0.9. Okay, so now X1, X2 are the input neurons. Okay, so whatever the input we are passing, it is going through the X1 and X2. And H1, H2 are the hidden layer neurons. Okay, and then O1 is nothing but the output neuron. Okay, and let me assume from X1 to H1, I'm assuming that weight is W11 is equal to 0.2, then W12, that is here X1 to H2, right? And that value is nothing but 0.3. Then the weight that is from X2 to H1. So I'm assuming that is W21, which is equal to 0.3, and W22, which is also equal to 0.3. So this is what the input weights, and then from WH1 to output, that I am assuming as WH1. The names W1 and W12 I am giving here for understanding any kind of variable name that we can use. Okay, so WH2 is equal to 0.9. So this is what our input. With this, we are going to proceed the backpropagation problem. Okay, so now as per the step 1, we will go with the forward pass, right? So when it is coming with the forward pass, first I will start with calculating the information that is passed to H1 from X1. Okay, so as per the diagram, how H1 gets the input from where? It is getting the input from X1 star W11 plus X2 star W21, right? Is there any bias that I have mentioned here in the problem? No. So with this only we are going to calculate now. So X1 is nothing but 0.35 star W11 is 0.2 plus X2 value is 0.7 star 0. Again 2. So this is what the value. So if I am calculating the net H1, the final output will be 0.21. Okay, so 0.21 is the output for net H1. But is it over now? No. I have to apply the activation function, right? So I'm mentioning that as out H1. That means after applying the activation. Here I'm applying the sigmoid. So 1 by 1 plus e to the power minus net H1, because this net H1 is the output what we received now, right? So 1 divided by 1 plus e to the power minus 0.21. So out H1 is equal to, so if I am applying 1 divided by 1 plus e to the power 0 minus 0.21, the value will be 0.5523. Most probably in all the problems here, I'll be going till the fourth precision. Maybe depending on the on your model, on your problem, you can choose any kind of precisions. Either you can start with the 0.55 or 23, or you can go with the sixth precision. Yes, you can go as you wish. Okay. So next time, starting with net H2, that is the input that is processed from X1, X2 to the H2. Okay. So for that again, I am depending on X1, right? So X1 star, X1 to H2 na W12 plus X2 star W22. So X1 value we know 0.35 star 0.3 plus 0.7 star 0.3. So calculate the value. It is coming around 0.315. So that is the value of net H2. But again, we have to apply the activation function, right? So that is what out H2, which is nothing but 1 divided by 1 plus e to the power minus 0.315. So if I am calculating this value, it is nothing but 0.5781. Okay, so at the end of this, we have calculated what is the output we are giving to X1 to X1 and X1 to H1 and H2. Okay, this is what we have calculated so far in the forward pass. Okay, now from the hidden to the output we have to calculate. So I am mentioning that I am going to mention that output layer as net Y1. Okay, because generally we used to represent the output as Y1, so I am using this. Any other variable names can be applied here. So here, what is the last value I calculated after applying the activation function hy1 star? What is the weight? First one, wh1 plus out h2 star wh2. So we know what are those values? 0.5523 star 0.3 is the weight, and then 0.5781 star 0.9. This is the weight, right? What is the value for net y1 is 0.68598. Okay, so again for this also I'm going to apply the activation function. So out y1, which is equal to 1 divided by 1 plus e to the power minus 0.68598. Okay, so the output is nothing but 0.6 is 51. Yes. Now we calculated till the output layer, right? So can we summarize here what are the outputs we got here? Because till starting from the input layer, we have calculated net H1, out H1. That means net H1 here it means before applying the activation function. Out H1 after applying the activation function. Similarly for H2. Similarly for Y1. Where this is nothing but my H means hidden layer to the output layer. That is what it represents. So first let us summarize the values what we have got here. Okay. And then we are going to calculate the error function. The error, how much error we are getting. For this, I forgot to mention the target. So let me assume the target. That means the original output that I am expecting here is equal to 1. Okay. And then what is the learning rate eta. Here I am assuming the learning rate to be 0.1. Okay, so let us assume it here, and now we will summarize all the values that we have calculated so far. Okay, so first one is nothing but, so first one is net H1, which is equal to, and then yes, here net H1 value 0.21, net H2 0.315, then out H1 yes. So this is what the values we have calculated so far. Now let us calculate. Okay, now we are going to calculate the error here. So error is nothing but we have seen 1 by 2, then target minus the predicted. Okay, so here the predicted value is nothing but 0.6651. So the target here is, let us assume 0.5 minus predicted is 0.6651. Okay, so here this 1.2 is actually a constant which we may keep or no need. Here, as I am involving only one output layer, I am ignoring it. Okay, so my value will be minus 0.1652. So this is what the error I got here, right? So my expected value is actually 0.5, but what I got here is 0.6651. So the difference between them is minus 0.1652. So this is what the error. So now with this error only, we are going to update the weight by backpropagating. Now, I got how much error it is. But as we have seen in this problem, how many weights were there? W11, then W12, then W21, W22, then WH1, WH2. See, 6 weights are there. So whether this error caused only by any one of these weights, no, we don't know which weight contributes a lot for this particular error, right? So we have to differentiate this error with respect to, that is, we have to calculate the gradient descent of this error with respect to all these weights and update it accordingly. So that is what we are going to see in the upcoming steps. Okay, so now we got the error. How much error we got? Yes, we got it. And then we got all the intermediate outputs when we are passing from the input layer to the output layer. Okay, now we are going to start the exact second step. Step 2, the backpropagation. So now we are going with the backpropagation here. Okay. Now I can represent the output layer here. somehow differently. Okay, that means out y1, that means after applying the activation function, and net y1 before applying the activation function, and I got some error here. Okay, and how did I got this outputs? Directly actually WH1 and WH2 involved in this. Now, when I am trying to backpropagate, I have to first starting from output hidden and then moving to the input. So I have to start like this. Error to the out H1, then from out H1 to net H1, then from this net H1 to WH1. So similarly, I can go with here from this error to the total error what we got here, right? So from this error to the out y1, then from this out y1 to net y1, from this net y1 to wh2. So what we are going to calculate now is we are going to calculate the total amount of error we got with respect to wh1, and okay, so the amount of error I got with respect to WH2. So, first step in our backpropagation is the output layer. So, I am going to work with the output layer. So, that is what here, from error to the out y1, then out y1 to net y1, net y1 to WH2. So, with this, I am trying to update the weights of WH1 and WH2. Okay. First, to calculate the gradient descent of error with respect to WH1. So, now we are going to apply the chain rule, what we have seen in the PPT. So, do error with respect to do net y1 into do net y1 with respect to yes, actually there's a problem. We have to reach this with respect to only out y1 at first. Out y1, then do out y1 with respect to do net y1, then dot do net y1 with respect to do WH1. So this is how we are going to calculate, right? So let me assume these parts as maybe this is the first part, this is the second part, and this is the third part. I have to calculate all these three parts to calculate this do error by do WH1. Okay, so let us start here. First, I will be calculating do error with respect to do out y1. Okay, so we know the formula for error, right? So the formula for error what we calculated there is target minus out y1. Out y1 means the predicted, right? So I'm going to write that formula as it is do out y1. Okay, with respect what I'm going to do here is target minus out y1. Okay, so how this out y1 is nothing but the predicted. Okay, out y1 is nothing but the predicted. That is why I'm using this formula. Okay, so now if I'm differentiating this target minus out y1 with respect to this out y1, we know what will be the answer, minus 1, right? Because it is a constant out y1 if I'm differentiating minus out y1, and hence the value will be minus out y1, right? So the output of this do error, now we have completed only the first part of our chain rule. Out y1 which is equal to -1. This is the output I got. So now I have to calculate this second part, that is do out y1 divided by do net y1. Okay. So now let us see do out y1 divided by do net y1. So out y1 is nothing but, we all know the sigmoid function what we are applying here. Okay, so do by do net y1 of 1 divided by 1 plus e to the power minus net y1. Okay, so because why I am writing here in this way, it is because out y1 which is equal to, which we have seen in the first pass itself, 1 by 1 plus e to the power minus net y1. So in the forward pass itself, we have seen this formula, right? So that is why I am using here. Now, when I am going to do this differentiation, first we have to understand the mathematical rule. Like if I can write like this, okay? So I can write this as y1 which is equal to, which is nothing but the sigmoid function, okay? Which can be actually written as the sigmoid function dot 1 minus sigma x, which is nothing but the sigmoid function, okay? So if I am writing this 1 divided by 1 plus e to the power minus net y1 dot 1 minus 1 divided by e to the power minus net y1. Now we are going to simplify this step. So if I am going with the simplification, so here I am starting, it is nothing but do out y1 by do net y1, which is equal to 1 divided by 1 plus e to the power minus net y1 can be written as out y1 dot 1 plus e to the power minus net y1 I am taking as a common denominator. So 1 minus 1 divided by e to the power 1 plus e to the power minus net y1, if I am differentiating, it will come like this. So which can be written as out y1 star. If I am taking this 1 divided by 1 plus e to the power minus net y1, it can again be written as out y1. Just I am simplifying the step, that's it. And then star e to the power minus net y1, right? Where this e to the power minus net y1, let that be as it is. Okay. So I'm using one simplification here. This is the place most of the time we used to make mistake. Maybe few people can work it out directly. Sometimes we will, when we are proceeding step by step theoretically how it actually works, we may get struggle. So that is why we are looking into these steps very elaborately. So out y1, which we know that can be represented as 1 divided by 1 plus e to the power minus net y1. Now here I am assuming this step as a. So let this be. Now when I am trying to simplify this one, see, it can be written as out y1 into 1 plus e to the power minus net y1 is equal to 1. So 1 plus e to the power minus net y1 is equal to 1 divided by out y1. Okay. Again, I can write it as e to the power minus net y1 is equal to 1 divided by out y1 minus 1. Okay. So now, see, remember here in this step, in this equation A, we have calculated out y1, out y1. These values are calculated in the forward pass itself. E to the power net y1, here I am going to substitute this e to the power net y1 with this 1 divided by out y1 minus 1. Or again, I can still simplify this and I can substitute this in the equation 1. Okay, so here e to the power minus net y1, which is equal to, I am taking here out y1 1 minus out y1. Now substitute this value in equation A. Okay, now I am going to substitute this in equation A. Okay, which is nothing but we have actually got out y1 into out y1, or I can write out y1 square. Yes, then 1 minus out y1 divided by out y1. So if I am cancelling this out y1 with this, okay, so what I will get is out y1. So if you can understand this concept very clearly, next time when we are proceeding with these steps, you can directly, instead of doing this many kind of simplifications, we can directly go with this out y1 minus out y1. With respect to this out y1, we are doing, right? So that we can write directly. Just how this step, actually how we are reaching this step, I have proceeded with all these steps. Okay, so which will be helpful for you when you are proceeding with any algorithm. Now, what is the value of out y1? So, which one we have already calculated, right? So, the value of this out y1 is 0.6651, right? So, 0.6651 into 1 minus 0.6651. Okay. So, its value is 0.2227, which I have calculated 0.2227. So what we are calculating here now is only the second part of our process. Out y1 divided by do net y1. So what about the third part? It is nothing but do net y1 divided by do wh1, right? So to calculate the net y1, what's the formula we used? Out h1 star wh1 plus out h2 star wh2, right? So now differentiate this with respect to the wh1. So as it is wh1, this part completely becomes constant. I am going to make it as 0. So the value will be out h1. Okay, so out h1 value we have already calculated, which is nothing but 0.5523. So that is the output of do net y1 divided by do wh1, right? So now actually we have done all these steps to calculate the value of dou error with respect to dou WH1. That is the gradient descent with respect to the H1. So the first value is nothing but -1. That means what we calculated is dou error with respect to dou out y1 into dou out y1 divided by dou net y1 dot dou net y1 divided by dou WH1. So now if you are substituting these values, first one is -1, then dou out y1 divided by dou net y1 is 0.2227. Then the value what we calculated the last into 0.5523. So the answer is nothing but minus 0.123. So now we have calculated only the gradient descent with respect to the hidden layer 1 to the output layer 1. Okay, so that is what we have calculated. Now to update the weights. Okay, to update the weight WH1. Okay, so to update the weight WH1, that means I am calculating the new weight of WH1 from WH old value minus the learning rate, okay, into what the value we calculated, the gradient value we calculated here with respect to dou H1. Okay, so now the old value of WH1 is nothing but 0.3 minus, assume the learning rate as 0.1 star, the value what we calculated is minus 0.123. So minus into minus it will become plus, so 0.3 plus 0.0123. So now the updated value is equal to 0.3123. So this is the WH new value. So what about the old value? It is 0.3. So from 0.3 we are updating the WH1 new value, which is equal to 0.3123. So similarly we have to calculate for the remaining weights also. So let us again move with the WH2. Okay, so WH2 updation, the second weight updation. So for that we have to calculate the error differentiation, the gradient with respect to the WH2. So what we have done earlier in the same way here, dou error with respect to applying the chain rule, dou out y1, then dou out y1 with respect to the dou net y1 into dou net y1 with respect to dou WH2. Okay, so now again like in the previous part we are going to calculate all these values. So here dou error with respect to dou out y1, there is no change what we calculated already, which is nothing but -1, and then dou out y1 divided by dou net y1 also we have already calculated, which is nothing but 0.2227, right? And then only this value dou net y1 with respect to dou WH2. So dou net net y1 divided by dou WH2, which is equal to, again to calculate the y1 we use the formula the same as the previous one, dou WH2, okay, into out H1 into WH1 plus out H2 into WH2. Now as we are differentiating with respect to WH2, obviously the output will be out H2. So the out H2 value which we have already calculated, it is nothing but 0.5781. So now substitute this here. Dou error with respect to dou WH2, which is equal to minus 1 into 0.2227 into 0.5781. So which is equal to minus 1 to, minus 0.1287. So this is the gradient descent of weight WH2. Now to update the weight WH2, to calculate the updated weight of WH2, again I am representing that as WH2 new is equal to WH old minus the learning rate into dou error by dou WH2. So the WH2 old value is nothing but 0.9 minus the assumed learning rate here is 0.1. We have to assume the learning rate somewhat minimum, because we are assuming here, if we are assuming it as high, means our model will learn very fastly and it may lead to overfitting or some other problems, underfitting or very small value in underfitting. So there will be some problems. So assume some reasonable weight which is not too much, similarly not too small values. Okay, so now this when we are calculating this, it is 0.9 plus 0.012, it is 1287. So 0.91287. So this is the WH2 new value. So now we calculated the new values of updated values of weight WH1 and WH2. Until now we have only completed from the output layer to the hidden layers. Now it starts with the hidden layer. So now we completed the output layer. Now we have to start with the hidden layer. Okay. So to start with this hidden layer again, let me redraw this diagram. So with x1, x2 we started. No need to worry about that. But when we applied the activation function, this net h1 and out h1, the neuron changed in this way, right? So similarly, net h2, out h2. Okay, and the output layer we have already seen, net y1, out y1, right? So now we have calculated, we have updated the value of WH1 and WH2, right? Similarly, we have to calculate, or we have to update the weights of this W11, W12. Similarly, W21, W22. This value I have to update. But is it possible for me to reach this value from this error? Okay, from this error to reach this W11, what I have to do is, from the error, I have to move to, let me say this is the error, error to out y1, out y1 to net y1, then from this net y1 to out to h1, then from out h1 to net h1, then only I can update the weight W11. So you got it, how the chain moves from that error to this W11. To update the weight W11, I have to start from the error to out y1 to net y1 to out h1 to net h1, and then to W11. So now we are going to update this. Okay, so formula as usual, we are going to apply the chain rule here. So dou error, that means how much the W11, the weight W11 contributes to this error, total error what we calculated. Okay, so to calculate it, as we have seen, I have to move like dou of error to do out y1 into do out y1 with respect to do net y1, then do net y1 to net h2, sorry, this should be out h1. So as per the diagram what we have reconstructed, so it will be do out h1 divided by do net h1, and then do net y1 with respect to do out h1, then do out h1, then do net h1 with respect to do w11. So this is what we are going to calculate now. Most of the values which we have already calculated here, this one already in the forward pass we calculated, and similarly this also 0.2227. So what we are going to calculate now is this do net y1 out h1 by net h1, then do net h1 by out do w1. Okay, so this is what we are going to calculate now. Okay, so shall we start here with do net y1 with respect to do out h1. So do by do out h1 of, what's the formula for net y1? We have done it as x1 into, sorry, not x1, it is out h1, right? I have misplaced it. It will be like out h1 star wh1 plus out h2 star wh2. Okay, so as we are differentiating with respect to out h1, so this part will entirely become 0. So the output is nothing but wh1. The original value which we initialized is 0.3. So this third part we have calculated now. Next step will be do out h1 divided by do net h1, right? So for this also we have seen elaborately how it will be calculated, right? So it will be out h1 into 1 minus out h1. So you refer the previous slides how we actually calculated this. Okay, so 0.5523 into 1 minus 0.5523. So the value value is equal to 0.2473. So this value also got calculated. Now the last one is do net h1 divided by do w11. Okay, so to calculate this do net h1 with respect to do w11. Yes, now to calculate the do net h1, we used the formula as x1 star w11 plus x2 star w21, right? So now we are doing with respect to w11, so this entire part will become 0, and hence this is nothing but x1 will be the answer, where x1 is nothing but 0.35. Now substitute this in our do error with respect to do w11. Okay, so if I am substituting, it will be minus 1 into 0.2227 into 0.3 into 0.2473 into this one into 0.35. So if we multiply this, the answer will be minus 0.0058. So if I am calculating the updated weight again, here W11 new is equal to W11 old minus the learning rate we assumed here is 0.1 into dou error with respect to dou W11, which is nothing but this value minus 0.0058. Okay, so if I am substituting this value here, W11 old is nothing but 0.2 minus 0.1 into minus 0.0058, which is nothing but 0.20058. So actually the original value of our W11 is 0.2. So after the updation, see very minute updation. So 0.2058. So as we got the error as the differentiation error in the sense the target minus the predictor value is the minimal value. The updation in weights are also minimum. Otherwise, we can see a considerable change updation in the new weights. So similarly, if we are calculating the other weights also, so W21 new will be 0.20115. Similarly, we can calculate for W. We can calculate for W12 new and W22 new. Okay, so we started with the certain values of W11, W12, etc. up to WH2, and then we have calculated the gradient descent with respect to the error, total error we got after the output layer, and we have started so from the output layer to the input layer, right? So in the forward pass, first step I started with the input layer, then I moved to the hidden layer, and then to the output layer I calculated the error. So as there is a deviation, I moved from the error to the output layer, then from the output layer to the hidden layer, and then from hidden layer to the input layer. By all the meantime, I was updating the weights W11, 12, 21, 22, then WH1, WH2. So this with this updated values of W11 new, W12 new, etc., we can again start the forward pass, that is from input, hidden, output, and then still we can get whether the error got reduced or not. If not, again we can propagate, means we can start the passes, okay, iterations, or we can stop with that. Okay, so this is the main use of our backpropagation. So hope you all have got idea about how this backpropagation work numerically, the mathematical background involved at the back of this backpropagation. Hope it will be helpful. Thank you all. Meet you again with some other new video. Thank you.